My name is Vlad. I'm going to talk here about some of the sensor and compute challenges for humanoid robotics. And I know some of you may wonder why should you care? So we believe that humanoids are one of the great next disruptions. They basically are robots designed to operate in human spaces. So there's a large market opportunity there for us. And obviously, we would say that we are in that business, but we are not the only ones, right? So lately, there's been a lot more traction on this. Goldman Sachs and Citigroup and a bunch of other investors throw out a lot of big numbers, and I'm not gonna say that they're right. The main point here is that there's more traction, more people believe in this vision. And obviously, we're not the only ones. There's an ever-growing number of companies out there. In fact, if any of you are following, investment news yesterday, Figure just announced a fairly eye-popping VC round. There's always been Boston Dynamics. There's us. There's Unitree. There's a whole bunch of other companies across the world that are investing in this space, and obviously, we all see something there. I think most of us believe in this vision that humanoid robots are going to be, at some point, are going to be everywhere. Just like most people believe autonomous cars are going to be everywhere, even though we're not quite there yet. So the way we see this is that the entry point to humanoids doing useful work is in the logistics and manufacturing space. That is one of the more structured spaces, one of the more constrained spaces, one of the spaces where the return for investment is more immediate. And that is what a lot of the humanoid robots companies are focusing on. And beyond that, the market grows. It could go into things that are a little bit less constrained, things like grocery and retail, construction. All these places, there are 30 jobs or jobs that go unfulfilled. There's millions of jobs that go unfulfilled in all of these spaces. And beyond that, obviously, anybody who's ever seen, like Jetsons or anything, it envisions a time when robots are going to be in the home. But we believe will happen eventually, just not anytime soon. I mean, the safety concerns alone are huge. But in order to get there, you can grow through all these spaces. So, I said why you should be interested. Why should you listen to what I have to say? Well, humanoids have been part of our company's legacy from at least 10 years. It started out in a university lab at OSU, Oregon State University, and then we've gone through many generations of humanoid robots, starting off with locomotion and then manipulation and vision, and more likely vision and sensing and compute. We have an integrated hardware and software solution, essentially meaning that we have the robot and we have the software to run it, and also along with it, all of the peripherals that go with it. Digit, which is our main robot right now, connects isolated manual and automated processes. It can provide scalable labor, and we can get things going within a few days, essentially. You can get a workflow going in a few days. We also have a full solution, including fleet management, security, user interfaces, all the stuff that makes a solution a solution. And I'm rushing a little bit through this because this is not the meat of the talk. I just want to provide a little background through this. We also just expanded into our what we call RoboFab, which is our new manufacturing facility in Oregon, near Salem, Oregon, which has a production capability of about 10,000. Obviously, we're nowhere near that, but it's provides us the room to grow, and it gives us the ability to control quality, and it provides economies of scale and tap into the global market. And our overall market expansion, like I just mentioned, we start off with some of the things that we can do now, which are around logistics, distribution, fulfillment, all those things. And then the idea is that to build on top of that, both mechanically and software-wise, to be able to provide, to expand into an ever-growing number of markets. All right, so, how are humanoids different than any of these robots, any of the millions of robots that are out there in the field right now? So obviously there's thousands of, if not more, of autonomous cars. There's millions of AMRs out there. There's there's even, legged robots like Spot and so forth. There's millions of drones, obviously. All of these are just under the type of robots. So why can't we just use what any of these are using? And in some cases we can, but there are some very key differences between most of these robots and humanoid robots. One of the major differences is humanoids are dynamically stable, or if you're half, glass half empty, dynamically unstable. But essentially, what this means is that the robot can walk over uneven terrain, can operate in dynamic environments, can deal with things like stepping on a banana peel for some reason, can walk outdoors, can walk inside. It's very dynamic in what it can handle. But this obviously is completely different than a wheeled robot, and for good reason. Also, humanoids can operate in dynamic spacing designed for humans. What does this mean? It means it can operate into narrow aisles, it can go up and down stairs, it can, operate in any of the spaces that have been designed for humans, which is all of the world, right? So we all take for granted that we can walk into this building, we can go up and down the stairs, we can go up and down, sidewalk and so forth. Those can be quite tricky for some other types of robots. And obviously you can design another type of robot that can operate in some of these spaces, but a humanoid is designed to operate in pretty much all of these spaces seamlessly. And then the other major factor here is that, unlike, let's say, an AMR, we are a mobile manipulator. Humanoid is designed by definition to be, to operate in human-centered manipulation in space. What does that mean? It means that basically we can lift at least 25 kilograms, right? So that is something that a logistic worker will do often, right? But we want to be at least that. Humanoids can pick up boxes or any object low off the ground or high off of a high shelf. And then we can also manipulate different sized objects. It could be something as big as a large box, or it could be something as small as a part. So anywhere in between, we have to operate in this rather large manipulation space. So that was just to set the scale. So what are some of our sensing needs, right? Why is this a little bit different than other robots? Well, first of all, one of the major differences, like I mentioned, is walking. We need to be able to, excuse me, we need to be able to know where we're walking and to be able to do things like footstep planning and be able to, just decide where we need to step. Then obviously we need to do mapping, navigation, localization, which is very similar to other robots, except that we have fewer constraints. We're not just moving on wheels. We're holonomic, we can move in any direction, we can bend, we can twist, we can do all these things. Obviously, we need to do dynamic obstacle avoidance, we need to detection classification of things we need to manipulate. We need to actually look at what we're manipulating, how we're going to pick up things, how we're going to pick those things up. And then obviously we need to also charge ourselves. So docking for both charging and data retention, all these things are important. And last but definitely not least, safety and collaboration are a huge deal, because without that, we are not going to, expand our use cases. So those are what we need, but what are some of the unique challenges? So one of the unique challenges compared to other robots is that we can self-occlude. What this means is that the arms and any of our appendages can get in the way of sensing. So we can't just have, the camera in front, a camera in the back, like an AMR, and that's it. Well, we can put a box in front of that. We can put an arm. All of that is a challenge. Also, we have dynamic stability, like we mentioned, and what that means in this case is that the robot can bend. Like if you're going to pick up a box that's on the floor, you're going to crouch and pick up the box. You're going to bend. It's going to have a totally different aspect ratio than what you had when you're standing. And if you're reaching up high, again, similar thing, right? There's also, obviously, you're operating in all these kind of human environments. There's lots of environment occlusion, a lot of lighting variations, a warehouse versus a machine shop or any of the other environments are going to have totally different illumination. You constantly have continuous vibration and shock. And this is one of those things that in the beginning people underestimate, but every time you walk, there's a shock that goes through the body. So every step is a shock that travels to the body, right? So you have millions and millions of shocks that go through the robot every day or through its lifespan. Obviously, a lot of dust and dirt gets collected. This is not that different than other robots, but again, we operate in more spaces, and also we crouch and do all these things that tend to accumulate more. We also pick up dirty boxes and totes and other things along those lines that transfer that to the robot itself. Oftentimes, we may have a camera somewhere in the chest or something like that, and we bump it a lot with the tote, transfer all of that onto it. Thermal variations, of course, from different environments, like I mentioned. And then obviously calibration can be a challenge with such a wide spectrum of cameras and such a large robot. And wear and tear, any robot gets this, but it feels to me like we get it more. Part of it is, we fall. It's one of the aspects that happen, especially during development. We obviously try to eliminate that, but and then just because we're a mobile manipulator and we walk a lot, like I mentioned, all the vibration, there's lots of wear and tear that needs to be accounted for. So every new generation, we improve that. And then, of course, the whole point is to operate in human spaces, but also among humans, hopefully. So that adds its own set of challenges. So I just wanted to kind of show some examples here. So obviously walking, mapping, navigation, obviously you see there, we need to be able to figure out exactly, we literally plan every step. And you need to be able to know that you can, you're safe to put a step there. And we also, this is the planning side of things. Obviously the dynamic stability part of this can handle unplanned, unplanned or unplanned divots in the road or anything along those lines. One of the videos I glossed over earlier showed actually the robot stepping through a thin piece of paper. It can handle all of those. There's lots of videos out there showing the robot just kind of stepping over just garbage in the street and so forth. So it can handle all of that, but you shouldn't have to, right? The whole idea is to essentially plan around things along like that, right? That is for the unplanned side of things. And then obviously we need to know where we are, where objects that we're trying to manipulate are, and all of that. Again, detection, classification, all those are a given thing. You need to be able to detect all the boxes and totes and other parts that we need to manipulate. Obviously we need to look at what we're planning, what we're trying to manipulate, and pick that up. And then the aspect that's kind of sort of new, it certainly hasn't been talked a lot by most of the companies in the space. I think we're one of the first that we're pushing this actively. The idea that we want to operate in human spaces means that we need to be safe around humans. Otherwise, we're stuck in a work cell, which doesn't make it really a human space. It just makes us a very expensive robot in a work cell. So, what does safe mean in this context? It means that we need to avoid any crushing, high-speed impacts, slide-in impacts, pinching, any of those things that can happen when our robot interacts with humans. So should a robot, our robot, show our robot like try to pick something and bend its arm and somebody sticks its hand in there, that would be a pinching hazard, for example. So this is from one of our live demos at, I believe, ProMat or Robotics, one of them. But basically, the robot has been running for many hours here, and it had an unplanned power error, right? The power went out. So the robot falls. And this is what happens with dynamically stable robot. If you had an AMR here, it would just pause on its wheels, right? And that has to be okay. I mean, it will happen, whether it's unplanned or planned in the sense of like, for some safety reason, you cut off power, right? Like a need stop kind of thing. But in order for this to be safe, we basically need to have continuous safe detection around the robot, right? So we need to know where everything is at all times, essentially. And, safe means essentially multimodal and certified. That's sort of a given there. And then continuous means we can't have any obstacles that are large enough to hide any we can't have any gaps that have any obstacles that are large enough to hide anything that we care about. The other issue with safety or, being safe is, like I mentioned, self-occlusion. If you place the cameras in such a way that basically the arm movement there occludes it, then you're creating a gap that is dynamic, but essentially that something can happen in that space if you don't account for it. And the other aspect, like I mentioned, is that obviously the robot can bend and tilt, and the fields of view of this are going to change. So this brings a lot of challenges because you can't just have a 180 camera in the front, 180 camera in the back, and you have a full coverage. Even in an MR case, you would still cut gaps on the side. But I'm trying to point here that it's not enough to do that, right? You need more coverage. So these are a lot of the challenges that we're faced, but I want to introduce something else that what I call the weight death spiral, which is, this is very similar to sort of like the rocket weight equation, right? So the idea is that any sensor, compute, payload, whatever you add to the robot increases the weight. That has the potential to increase the actuator size because you need more power to lift yourself, just also to maintain the characteristics of lifting 25 kilograms and so forth and doing manipulation. That increases the amount of structure you have to add to the robot. You have to, in order to have a heavier motor, you need more structure around it to protect it. That increases the battery size. You can't reduce the runtime. You have to still run at least 90 minutes, 2 hours, whatever, plus with a very short recharge. That increases the weight. And so forth, right? So the point here is that anything you add to the system starts this spiral of like weight death spiral, right? So it has potential to do this. So it can be very tricky to manage this. And it also emphasizes that basically for us, we don't want to end up here, right? So and
although that would be cool.
I think I just baited everybody who laughed at that, but this is from Robocop from the 80s. But anyway, essentially, you don't want to end up with a really huge robot to be able to accommodate all of these things. You want to go the other way. You want to sort of unwind that spiral and try to make your robot as light as possible, which reduces the actuator size, which reduces the battery, and so forth, right? It also makes safety a lot easier if the robot is lighter. Though I will say that robot being light does not make the robot safe. I didn't want to put it in here, but I'm sure a lot of you, or maybe not, have seen this video of one of the little G1 Unitary robots kind of like swinging its arms when it's lost control. That is not safe. Yeah, so this emphasizes that basically size, weight, power is not just important, it's critical to our design of the robot. So, what are some of the sensing modalities that we use on humanoids, but really any robot in general? Obviously, depth in any variety, stereo, light modulation, time of flight, LiDAR, any of those things are highly used on pretty much any robot, including ours. EO cameras, such as like RGB cameras and so forth. Obviously, again, these two are the main modalities used on most robots for good reason. They are time-proven and very useful for pretty much every task we do. But there's these other modalities that are also becoming more useful. They've been used obviously in cars and other outdoor robots, such thermal radar, especially now with like the 4D radar, like the imaging radar provides more capability. Sonar and ultrasonic have always kind of been used in some fashion, but nowadays there's even a 3D ultrasonic, which is also being more useful. Inertial sensors are obviously used a lot. IMUs, gyroscopes, accelerometer, and so forth. And then obviously some of the things that are a little bit more unique to legged robots in general. So not just us, but also like things like quadrupeds and so forth. Force torque sensing, pressure sensing. Those are also used, though they are a little bit less used because of the cost and because of the added weight they can add. But as those are coming down, more of these are we use anything that we can if it doesn't add too much to the robot. This is just an example of our last generation of robot where we have a LiDAR, an IMU, a whole bunch of depth cameras, force torque sensing, and there's some other stuff that I didn't bother mentioning here. So obviously for most startups, robotic startups in the beginning, they tend to gravitate towards off-the-shelf sensing. It's easy to use. So here, the automotive sensors have been great to some degree. They're reliable and proven. Many of them have ASIL ratings. Many of them have IP ratings. They come with better interface options than things like commercial interfaces of MIPI, GNSL, T1. These are very reliable and good options. But usually they're optimized for a car. So, you add another kilogram to a car, who cares? You add another kilogram to our robot, that's a big deal. They also tend to be quite expensive. The volumes are not quite there yet. And they're optimized for long range. So a LiDAR might be optimized for 100 meters or 200 meters. I don't care about that. I mean, basically for 200 meters is already way outside of my range of things, right? So all of that power and getting that range is useless to us. So you end up with fairly large sensors. They're good, but they're not quite optimized for what we need. Same for for AMR and AGV sensors. There's also there's also a bunch of sensing there that we can use, but there's been, for whatever reason, even though AMRs have been around for a while now, and there's millions of them out there, a lot of them still use sensing with things like commercial interfaces, which are problematic, right? Like things like USB, even DD can be problematic for a robot like ours. And they're not nearly as rugged for vibration and shock. Something on wheels doesn't have the same level of requirements for vibration. And we've also talked to some vendors who have, let's say, a solution for we can detect obstacles natively in some ASIC on the sensor, but often they assume stability. Like they assume that basically the ground plane is stable. Like we don't go up and down. That's not very helpful for us. And it makes those assumptions make sense. I mean, if you're marketing to AMRs, that makes sense. So what do we want? All right, I mean that's why we're here. Like, what would we want? Well, obviously, top of the list is lower swap C, and I showed two examples here. These are real. Like the first, both the top one are two time of flight cameras. One is, and they have different markets, so it's not like one is better than the other. They're just aimed at different markets. The one on the left is 785 grams. The one on the right is 35 grams. So that makes a huge difference to us. Obviously, they're meant for different ranges. They operate at different ranges. The power consumption is much higher. There's a lot more illumination on the one on the left because it's meant to operate in a works, over a whole work, so on and so forth. The one on the right was actually designed for like headsets, for example, right? So it is, or some similar environments, or like a drone or something like that. Different requirements, but again, like this is the space we kind of want to see. We want things to get smaller, or at least provide a range of options where we have maybe something in between, maybe something that has a little bit more range. The same thing with LiDAR, right? So something designed for cars or something like that, 470 grams, like half a kilo, who cares? Doesn't matter. 16 watts, not a big deal. But something that's like significantly smaller, 250 grams and 7 watts, I can put 2 of those at least on for the same cost and provide way more coverage. So lower SWaP-C, obviously very important. We want to be able to trade off range resolution for reduced SWaP. Customization is very important. Obviously, we're trying to package into as small of an area as possible. Interface options are important here. A lot of times somebody will come out with a new sensor and it will only have like, USB or Digi or something like it, or even just GNSL or something like that. Whereas maybe we can just do MIPI directly, or maybe we can do some other type of interface directly. Enclosures should be optional to some degree. I mean, like it's good to have IP ratings, but if we're already including it into an IP rating something else, then that's added weight, or we have to do extra work to take it out of its enclosure, reduce it, all its testing goes out the window. And different power modes, honestly. This is one of those things that should be fairly easy win. If just enabling that in the firmware to be able to run at a lower power with reduced functionality would be a huge boon to a lot of these sensing. This is a big ask, but obviously functional safety would be fantastic, or at least some path towards that. We're talking to a lot of vendors differently, and it's one of those aspects that we get it. It's very complicated. There's a lot of regulatory bodies, different certification in the US, different ones in Europe. But it would be good if there's a roadmap for that, or at least something like, hey, we can partner together to certify something. And this is usually not an issue for sort of off-the-shelf hardware because they usually have a lot of platform support for things that are common. But we've talked to some vendors where you can get like smaller parts, more industrial parts, and when platform support there can vary wildly, right? So they may support, let's say Jetson maybe because it's become fairly prevalent, but they may not support something else. And modular SDK is always nice. I mean, like the ability, there's some vendors who will create SDKs that are like too heavy. Everything is inclusive. Like you have to use everything they provide to be able to get data out and then do the pre-processing and do all this processing. But we don't always want that. Sometimes we just want the raw data and we want to like discard everything else. So if everything was modular, that would make it a lot easier. So far we've talked about sensing. So, compute-wise, obviously we have a lot of sensors to compute. And not just that, it's latency critical, right? So everything has to be real time. Well, not everything, but most things. I mean, like we have to decide where we put a footstep within milliseconds. We have to decide if there's an obstacle we have to go around within tens of milliseconds and so forth. We have to decide how we pick things up in the same time range. So, and all that has to run, like I said, real time, has to run on edge, like on the actual platform itself. You can't really offload any of that stuff. And these are some of the things that we have to do. Controls, like basically where each of the motors go, footstep planning, path planning, state estimation, mapping and navigation, pose estimation, dynamic obstacle detection, classification, manipulation, all of these things, right? And this is it's probably not even like fully inclusive. I just kind of put on here the most most common things. And on top of this, this is all the stuff that's critical to the operation of a robot, critical to operation doing the work, the workflow it's supposed to do. There's a whole slew of other things that most people don't think about that also take compute on the platform. And these are what I call asynchronous compute because they don't have to happen in real time. But there's an aspect of human robot interaction. Like it could be as simple as just blinking a bunch of LEDs to signify the task you're doing, or like red light, green light on its shoulders, or things along those lines, or showcasing an area of operation where you're moving. But you have to signify some way to humans what you're doing because it's a very important, A, for safety, but also for just normal flow, operational flow. Data collection and logging, this is huge. I mean, even just for debugging purposes, but also for obviously collecting data for better models and so forth. I mean, that's part of a lot of the secret sauce. Fleet management, security, fault detection, calibration, incident recovery and management, and all debugging flow. Right? All this takes a little bit of extra computing. So, this is one of those things where a lot of robotic companies either fail or just stay on the left side, right? Crossing the compute efficiency chasm. Pretty much everybody starts on off-the-shelf hardware, like an x86 CPU, some discrete GPU, some dev boards and kits and stuff like that. That's easy. You can buy them anywhere. You can develop software for them easily. You put a prototype together, you build that. And it's for prototype systems that's relatively inexpensive. Of course, when you start building thousands or millions of these, those costs add up quickly, and plus, like, they're not as customized and reliable as a fully optimized solution. Also, you're wasting a lot of power. I mean, the compute efficiency of that type of system versus something like your phone are quite different. So, pretty much every robot company wants to get to the right side. It's a matter of how easy it is to get there and how much effort you're willing to spend in, right? So there's different steps along the way, and these may be not necessarily in the right order depending on your particular path, but you can maybe go from a discrete CPU and GPU to combined version. I put NVIDIA Jetson in there because it does corner a lot of the market. There's obviously dedicated processor with like some of the neural network chips that we've seen here, and also other places where you can do more power efficient neural network computation. Phone processors and with AI functionality dedicated, and then obviously you can get all the way to like custom chips and for everything, right? Like that would give you the most power efficient computation, but that is obviously the highest level of effort. And crossing this chasm is very hard, obviously. It requires a lot of partnering with other companies. Most robotic companies aren't going to have the expertise to, that design any custom DSP code or any IP, like FPGA code or any of that stuff. They can hire for that, but most of the times it's probably more efficient to just work with somebody else. It's also obviously very expensive. I mean, like designing new chips and stuff like that takes a lot of time and effort and cost. So anything we can, so how can you help us cross this, efficient time? The biggest barrier, honestly, is support to some degree. I mean, a lot of the times, it's not even about like having, obviously, documentation and so forth are very important, but even just providing consulting and customization services. Oftentimes, companies like ours are willing to outsource this. It's just that it's hard to kind of work with somebody to get the right solution. You end up oftentimes you'll work with a chip company who then will forward you to a third company who might forward you to a fourth company. Things get a little bit messy. Obviously, dedicated support. I'm not going to name here any big companies, but oftentimes, big companies starting with a Q that might that basically outsource all support to like third party and fourth parties and so forth, right? Essentially make it very hard to get the right answers to just something that usually you get access to the right engineer, you answer in 15 minutes, but you might spend a week trying to figure it out. Obviously, tooling to convert models from common architectures to accelerated chips are very important. It's just the fact that life pretty much everybody develops in CUDA. I mean, so from there, converting to Onyx, converting to some of the other formats, and then basically optimizing for accelerated chips. That is where people get stuck. That's where companies sort of like throw in the towel. Because they may have a very fancy model, they've trained on millions of data points and all these things, and then they start, use it up a lot of power, let's start in a whole effort, let's make it more efficient, let's quantize it, let's do this. They start converting it to some new chip, and then they realize, oh, this instruction is not supported. And it wasn't really documented well anywhere, right? So that was where a lot of this fails. So having the up-to-date documentation with the equivalent operations, if you don't support a particular operation, maybe provide how you can do the conversion, right? Provide that support. Try to grease the wheels of that conversion. Profiling tools. This is also huge. The tooling in this space is either very specific or not very user-friendly. Let's put it out. Again, another reason where support helps. Deployment tooling is also another thing that kind of gets overlooked. It's one thing to optimize something for a particular chip, but it's what do you have to do when you have to do that for 1,000 robots, 1,000,000 robots? And then integration with common platforms. It's good to see that the AI chip companies are trying to partner with bigger platform, because that's what you're not going to end up using the AI chip by itself. You're going to end up using it with another like CPU platform or some other platform, and having that partnership already so that it's all kind of integrated makes it a lot easier to integrate. And don't forget about non-AI acceleration. Like, everybody's so focused on AI right now, but so much of the sensor processing happens before you even do any of the neural network stuff, right? So having optimized blocks for doing things like on distortion, for example, something as simple as that, or just conversions and resizing and all those like little operations, right? Like that would normally use up CPU power. If we can just optimize those, you end up saving quite a bit. And that's it. Thank you.